Let's see the free space propagation model. The free space propagation model is used to predict received signal strength when the transmitter and receiver have a clear, unobstructed line of sight path between them. Satellite communication systems and microwave line of sight radio links typically undergo free space propagation. As with most large-scale radio wave propagation models, the free space model predicts that received power decays as a function of the TR separation distance, raised to some power, which means a power law function. The free space power received by a receiver antenna, which is separated from a radiating transmitter antenna by a distance, d, is given by the free space equation. The equation can be used as PR of d, which equals to pt gt gr lambda square over 4 pi square d square L. The path laws, which represent signal attenuation as a positive quantity measured in dB, is defined as the difference in decibel between the effective transmitted power and the received power, and may or may not include the effect of the antenna gains. The path laws for the free space model when antenna gains are included is given by PL of decibel, which equals to 10 log PT over PR, which equals to minus 10 log GT GR lambda square over 4 pi square D square. When antenna gains are excluded, the antennas are assumed to have unity gain, and path laws is given by PL of decibel, which equals to 10 log PT over PR, which equals to minus 10 log of L lambda square over 4 pi square D square. The Fraunhofer distance is given by dF, which equals to 2D square over lambda. For example, if PR is in units of decibel per meter, the received power is given by PRD decibel meter, which equals to 10 log PR of D naught over 0.001 watt plus 20 log D naught over D. In example 2.3, find the far field distance for an antenna with maximum dimension of 1 meter and operating frequency of 900 MHz. The largest dimension of antenna D is 1 meter, operating frequency is 900 MHz, and then it's given lambda, which equals to C over F, 3 times 10 to the power of 8 meter per second over 900 MHz. Then exchange the megahertz into the hertz. 3 times 10 to the power of 8 meter per second over 900 times 10 to the power of 6 hertz, which equals to 0.33 meter. Using a far field distance as dF, which equals to 2 times 1 to the power of 2 over 0.33, which equals to 6 meter. Example 2.4. If a transmitter produces 50 watts of power, express the transmit power in units of A, decibel meter and decibel watt. If 50 watts is applied to a unity gain antenna with a 900 MHz carrier frequency, find the received power in decibel meter at a free space distance of 100 meter from the antenna. What is PR 10 km? Assume unity gain for the receiver antenna. We have a solution. Transmitter power is given PT, which equals to 50 watts. Then carrier frequency is given 900 MHz. Then PT dBm, which equals to 10 log PT the megawatt over 1 megawatt, which means 10 the logarithm of 50 times 10 to the power of 3, which means we change it. The watts is become into megawatts. Then 47.0 dBm, decibel meter. When we see decibel watt, 10 log, which means PTW over 1 watt, which means PT, the first is the milliwatts. Then PT watts over 1 watt, 10 logarithm of 50, which equals to 17.0 decibel watts. Then the received power can be determined using this equation. PR equals to PT GT GR lambda square over 4 pi square DL D square lambda L. PR equals to 50 times 1 times 1 times 1 over 3 the whole square over 4 pi square. Then times 100 square times 1, which equals to 3.5 times 10 to the power of 6 minus 6 watt, which means 3.5 times 10 to the power of minus 5 milliwatts. Then PRDBM, which must be 10 log PRMW milliwatts, 10 log 3.5 times 10 to the power of minus 3 milliwatts, which equals to minus 24.5 decibel meter. The received power at 10 km can be expressed in terms of decibel meter using this equation, where D naught which equals to 100 meter and D which equals to 10 km. PR as given there. Then what we're going to do here is PR is 100 meter and 20 log is 100 meter and changes to meter, 1000 meter. Then it's become minus 24.5 decibel meter minus 40 decibel, which equals to minus 64.5 decibel